and this is what I talk about in part 2 in the second session, including PC algorithm, FCI, the basic idea of FCI algorithm, and I'm going to talk about GS method, which is the typical score-based search method, causal search method. And then we'll have a very quick look at some extensions of the constraint-based method for causal discovery to deal with the practical issues in complex situations. Okay. Now, last time I asked you, do you know how many decks we have right here in this case? How many decks can be represented by this pattern? Remember, yes, the answer is 4. After the talk, I saw and some of you gave the answer 4. Great, it's 4. Note that the directions of different edges are coupled, right? Because we cannot have fake these structures. Very good. And then this is particularly important because a lot of people say, yeah, you cannot do causal discovery because there can always be confounders, unmeasured derived common causes. But here with those examples, you can see, yes, right here, we are sure that there are no confounder behind the variables. And we are sure that X3 is a derived cause of X4. And sometimes this is known as Y structure because you can see it's Y. And in this case, we know there must be confounders. And we know that there are no direct causal relationship between the two variables, X2 and X4. Good. And then right here, you can see an example of application of the Y structure. You may see the detail later. Let me just give the key information right here. By making use of conditional independent-based methods, they discovered the Y structure and concluded that the pH value of water or acidity of water is the only direct cause of the biomass of the plants near the electric company. So that's very strong conclusion. And later, this claim was verified by intervention-based analysis. So causal discovery methods are really useful. You can discover very strong information by making use of conditional independence relations. And then basically, PC algorithm contains those ideas regarding how to detect confounders and how to find the causal relations in the presence of confounders. And as a consequence, we cannot use patterns right here. You cannot use a pattern to represent the output of of FCI. Why? This is because if the original set of variables follow a DAG, then the observed variables as a subset of the whole variable set cannot be represented by, usually cannot follow a DAG. That's why we have to find something more general to represent the relationships between the observed variables if you allow confounders. And right here you can see it's different from pattern in which we have 3 possible edges. Now we have 5. And you don't need to really see the detail of FCI, which is very complex, but it's nice to have a very nice interpretation of the result of the output of FCI. So right here, you can see, you see this pattern before, you see this edge before, this edge before. Right here, X1 and 2 are not adjacent. Here, X1 is the cause of X2. And here, if you see this, this means there's a latent confounder, or there are latent confounders for X1 and X2, and that there's no direct causal relationship between X1 and X2. And right here, we have circle. What does it mean? Circle just means that right here, we can have either an arrow head or arrow tail. So either head or tail. If it's a head here, then we can say, oh, they are confounders for X1 and X2. If this is arrow tail, then we can say X1 is the cause of X2. This is how to interpret the output of the FCI algorithm. Okay, now remember this example. This is the second example. Right here, we have 4 variables, right? And now we have a confounder. We generate the data from this graph. Suppose we have enough data. So what do you think would be the output of FCI on the observed variables X1, 2, and 3, and 4? So actually it's this. We are sure that there are confounders between C2 or X2. I use different, sorry, I should use X. So we know there must be confounders between or behind X2 and X4. Right here, we don't know. What does it mean? This means, oh, C1 may be the cause of C2, or there could be confounders for C1, C2, or a combination of them, right? We don't know. From this example, you can see that the FCI result is, first of all, asymptotically correct. Second of all, it might not be very informative. Why? Because whenever it's possible to have a confounder, the result will tell you that, yeah, so you can see it's possible to have a confounder. In other words, we don't have very many directed edges, just directed to show that one variable is a direct cause of the other. Okay, in some cases, for instance, if you have Y structure, then you are sure that X3 is a direct cause of X4, but that does not happen very often. That's why we say the result of FCI is correct, but it's not very strong. Later, you can see we can make use of other methods to make the result, causal discovery results, much stronger. Okay, so now you see how PC works and the basic idea of FCI. And now let's have a very quick look at another set of methods known as score-based search methods. And this is the procedure. You have data right here, and you have a set of candidate causal structures. And then you want to see which of them gives the best score according to the data. And then you just want to find the best one. So this is score-based method. So in particular, GES, greedy equivalence search, is very popular. This method achieved a lot of attention, a lot of applications, and a lot of attention in the community. So here the assumption that follows. First of all, we assume the score that is used for search, for causal search, is equivalent, meaning that it assigns the same value to equivalent DEX, to Markov equivalent DEX. Second of all, the score is locally consistent. So if you add an edge that can eliminate some false independence constraint, then the score would be better. And finally, the score is decomposable. The total score is the sum of the individual scores right here. Each term corresponds to a particular random variable as the effect. For instance, BIC score satisfies those conditions, and BIC score has been used in GS. So this is very tedious, but basically, just like many greedy search procedures, GS has two steps. The first step is forward search. The second one is backward deletion. So in the forward step, we just keep adding edges until we cannot further improve the score. And then we go backwards. We just want to delete those unnecessary edges. Here you can see examples. Right here, suppose this is the ground truth. Then the GS result may be like this. So suppose the correlation between X and Y is strong. First, we have this edge, and then we add the second edge. Here, we just consider all possible equivalence classes. That's why in the first one, we don't have direction, because this is the representation of the equivalence class. And the second one, we must have the directions. Why? This is because we have this structure. And then we will stop because we cannot add any additional edges to further improve the score. And we do the backward deletion procedure. And in this case, we cannot get rid of any edge, so we will stop. Second example, right here you can see X causes Y via a lot of other variables. So in this case, let's suppose all those causal parameters are similar and are positive. And then you can imagine that the correlation between X and Y could be very high because of the multiple pathways right here. And then it's not surprising that first, GS will add the edge between X and Y because the correlation between X and Y is very high, right? If you add this edge, you can improve the score most. And then you can keep adding edges. And finally, you can see that after the first step, you are going to have an extra edge, which is between X and Y, right? That's why we have to use the second step, which is the backward deletion process. So now we can see, oh, given the remaining edges, the edge between X and Y is not useful. we can just get rid of this guy. As a consequence, after that, we can get the correct equivalent class of the causal DAG, original causal DAG. So this is the GS method. And then let's have a quick look at some extensions. First, in many cases, in many applications, especially in healthcare, we have missing values, right? In a data set, we have a lot of missing values. And you have to extend the method to handle missing values. And first of all, we observe that the conditional independent relations in the data are very sensitive to the missingness mechanisms. What does it mean? It means that if you just consider the pairs of variables or set of variables and just make use of the complete record in which you don't have missing values, then the conditional independent relations right here could be very different from the conditional independent relations implied by the original true DAG. Okay, this is because of missingness causal mechanism. Right here, you can see some missingness graph. So this is one way to represent not only the causal mechanisms between the given variables, but also why and how the data are missing. For instance, here in the first graph, Ry is the indicator of whether the value of y is missing. If the value of y is missing, then Ry has value 1. If not missing, then the value is 0. Okay, so this is the variable now. In this case, Ry, the random variable, missingness random variable or missingness indicator, is independent from all those observed variables. In this case, we say it's missing completely at random, MCR. And in this case, you can see the missingness indicator of y depends on w. W does not have missing values. Then this is the case of missing at random. And in the third situation, Ry depends on w, and furthermore, w also has missing values. In this case, we say it's missing not at random. In all those situations, we can do something to recover the conditional independent relations in the whole population by analyzing the records with missing values. And this is why we can still do successful causal discovery even if we have missing values. So if you are interested, you may have a look at this paper. Okay. And the second problem is about non-stationarity or heterogeneity of the data. So in practice, very oftentimes we have either non-stationary data where the distribution of the data can change over time, or heterogeneous multiple data sets where the distribution of the data can change across different data sets because of different collection conditions or experimental conditions. For instance, if you have observational data and interventional data, clearly distributions are very different, right? Because of interventions. So right here, we have to leverage all data sets or all data together to find the causal information. And in this case, we can benefit from one very important property of causal systems, which is about the relationship between causal modeling and distribution shift. So basically, causal modeling and distribution shift are heavily coupled. What does it mean? So if you know that X causes Y without a confounder, then we know that the process to generate X, the cause, is completely irrelevant to the process to generate Y from X. So this is known as, again, modularity. We have irrelevant or independent modules to generate the data, right? In other words, if you have non-stationarity or if you have distribution shift, then the distribution of cause and the distribution of effect given causes would change independently. Otherwise, you have to explain the dependence between them. You have to introduce common causes, right? So yeah, probability distribution of cause and the distribution, conditional distribution of effect given cause would change independently. And right here, you can see, yeah, if you know it's causal, you can say something about how the joint distribution can change. And on the other hand, if you see the distribution shift phenomenon, then you can verify that and you can find the causal information without much difficulty. That's what we are going to make use of to discover causal information from non-stationary or heterogeneous data. here we assume that the causal structure can change over time across data sets, right? You can see, oh, causal strength can change, and sometimes we have extra or missing edges somewhere. Doesn't matter. So in this case, we can find the whole causal graph, and also we can find where the causal models can change. So right here, suppose we have 4 variables, V1, V2, V3, and V4, right here. And suppose we have a confounder, G, C. Right here in this framework, we assume the confounder can be written as a function of the surrogate variable. The surrogate variable is either time index for non-stationary data or the domain index if you have multiple domains or multiple data sets right here. So now we just have observed the data for V1, 2, 3, and 4. What can we do? Or what should we do? First, we want to determine for which variables the causal mechanisms change. We can do so. Now, first step, we say, oh, V1, V2, and V4 have changing mechanisms. And second, we want to find a true causal skeleton. With our method, yes, we can, even if there can be confounders. And third of all, we want to find the causal directions. And here we benefit from the property that probability distribution of a cause and probability distribution of an effect given cause change independently, right here. And finally, if you know that the causal mechanism for a certain variable changes over time across domains, you want to find a low-dimensional representation of the changes, right? To see, oh, why and how the mechanism change. So we developed a non-empirical method known as the kernel non-stationary driving force estimation to find such representation. Okay, so now to make it very short, first we apply some constraint-based method like PC to the variable set, to the set of observed variables, and also the surrogate variable C, the index variable. And then any variable that is adjacent to C will have changing mechanisms. Okay, so this is very cool because it's very simple. We can immediately determine for which variable the causal mechanisms change. And then we want to find a direction with the independent change principle. So basically, we know what it means. And then this is the generalization of invariance. Because if one of them does not change, then clearly they are independent because a constant is independent from anything. And this independent changing principle is generally violated for wrong causal models. And then here you can have a look at some special cases. In this case, we have 2 variables, Vk and Vl. One of them, which is Vk, is adjacent to C, meaning that the causal mechanism for Vk changes. Okay, and then we can immediately determine the direction between Vk and Vl. So if C, the index, and Vl are independent, given a subset of variables which do not contain Vk, then we know, oh, this is a V structure. Both of them point to Vk. In other words, the distribution of Vl will not change. We say this is the invariant cause. And furthermore, if C, the index, and Vl are independent given a variable set containing Vl, then we can say, oh, this is a chain structure. Because we know C causes Vk, then we know the direction between Vk and Vl. Vk is the cause of Vl. So in this case, you can see although the distribution of Vk and the distribution of Vl changes across domains or over time, the causal mechanism from Vk to Vl will not change. So we say this is an invariant mechanism. Essentially, invariance is just a special case of independent changes. And if both variables are adjacent to C, then we just need to verify whether they change independently, whether this condition holds true. And because this property, we can find the directions. Okay, right here you can see application. We analyze the daily returns of more than 80 variables in NYSE, New York Stock Exchange. And right here you can see we can find the directed graph. And furthermore, we can just visualize the non-stationary driving force of the change in the mechanisms for different variables. And this is for USB company. It's interesting because we can verify that this driving force is clearly associated with the risk in the market. Right here, this is 2008 financial crisis, and this is 2007. You can see actually in 2007, the risk is already very high, but in 2008, the risk is extremely high. That's why we had the financial crisis. Okay, so from data daily returns, we can really analyze their causal relations, and we can explain why the mechanisms change over time. So right here in this part, we can see that conditional independent relations can be used to discover causal information. We see what assumptions are needed. Essentially, we need a causal markup condition and faithfulness assumption. And then constraint or conditional independence constraint-based methods were proposed, developed by pioneers in the community, because those methods were developed at the very beginning of the 1990s. Some methods can handle confounders. However, later you can see we can, under some further assumptions, we can handle confounders in a better way. And in practice, if you do causal discovery, you have to analyze the given data, observe the data. The observed data were generated by not only the underlying causal process of interest, but also the sampling process, measurement error, and so on. That's why we have a lot of practical issues to deal with. So right here, you just saw that how we can deal with missing data and how we can deal with non-stationarity or heterogeneity in the data. Okay, now let's have a look at part 3. We are going to see those methods and ideas that were developed in the last 15 years, more recent. So in this part, first I will present linear non-Gaussian causal models. You can see why this model can be identified from data uniquely. And then we are going to have a look at the non-stationary functional causal models and see how we can discover causal relations by making use of them. And finally, we will see some extensions, including how to analyze the causality in time series and how to learn hidden causal variables and their relationships, or the hidden causal representations from data. And also, as a special case, we'll see how we can deal with the measurement error in the observed variables. Okay, probably I should just pause for half a minute. Is there any question regarding conditional independence constraint-based methods? Currently, no. Okay, so if there are no question, I will just give me a second. No one raised the hand. Okay, let me just go ahead. Right here, you can see the scatter plot of the data pairs in the Tübingen dataset, Tübingen causal effect pairs dataset. So in the first dataset, we have x1, x2, two variables. We have realizations of values, and this is the scatter plot. Now, if you make use of a conditional independent-based method, usually you have to make use of at least 3 variables because you want to make use of conditional independent relations. And now we have 2 variables. Can we discover which variable is the cause? With the traditional method, you cannot, right? So what can we do? Then you can see that we have to assume something about the causal mechanism. And then all of a sudden, a lot of information about the causal mechanism can be discovered from data. By the way, the 2 variable case is the fundamental case in causal discovery. Why? Because if you can find a causal direction and a causal model for 2 variables, then no matter how many variables you are given, you can just condition other variables in the right way, and this will become a 2 variable problem, right? That's why the 2 variable problem is really fundamental. Okay, so here you can see a causal process. Rain causes the wet ground. So we know, when we say this is a causal process, we mean the following thing. If there are no common cause for rain and wet ground, then the generating process of the cause, rain, would be completely irrelevant to the generating process. from rain, the cause, to the effect, weather ground. Right here, that means the generating process of X and the generating process from X to Y are completely irrelevant. E, the error term, is involved in the second process. That's why X and E, cause and noise, would be independent. Okay, so, and this gives the definition of functional causal model. So we can just represent the effect as a mathematical equation or mathematical function of the direct causes and noise. The noise is the omitted factors, right? We cannot measure everything. And the noise is represented by E. And here, X and E are not are independent. If X and Y do not have other common causes, if there are no common causes, then X and E shouldn't be related in any way. That's why X and E are independent. So this is a functional causal model. This model is very general, right? It's just a functional form. Without any assumption on the functional form, we cannot make use of this representation to discover causal information. X and Y would be symmetric. However, if you introduce some structural constraint on the function f, all of a sudden, you can find that, X and Y are not symmetric. Only one direction between X and Y admits some properties for the causal process. Okay, right here, you can see three typical functional causal models that can be used for causal discovery, because the relationship between X and Y is usually not symmetric according to those models. I mean, if the data were generated by those models. The first one is the linear Non-Gaussian cyclic causal model. So effect is a linear function of the causes and the noise. And here we assume not all noise variables are Gaussian. Later you can see the example and how we can solve the problem. The second one is called the nonlinear additive noise model. So right here, the effect is the nonlinear function of the cause plus noise. And the third one is called post-nonlinear causal model. It was first proposed in 2006 to solve some problem in finance. So right here, we have additional distortion function, F2. Later, you will see that this function is actually very useful. Okay, now let's try to see why we can go from correlation to causation in the linear case. Before that, let's just remember the definition of independence and conditional independence. So when we say X, Y are independent, we mean that the joint distribution or joint distribution function or joint probability density function or mass function can be written as the product of the individual ones. In other words, the conditional distribution is the same as the marginal distribution right here. So what that means? It means X is not relevant, or X has no information about Y, or Y has no information about X. So similarly, if X and Y are conditional independent given Z, then we have independence between X and Y for any value of Z. Okay, this is conditional independence. So now let's have a look at the two examples. Right here, in the first example, you can see the red data points, the scatter plot. First of all, we know that they are uncorrelated, okay? But do you think, remember, the covariance is just the expected value or averaged value product, right? After you center the data. That's why you can see, the average product of this variable and that variable would be 0. And this is right here, this is the origin. So they are uncorrelated, but do you think the two variables are independent? Yes or no? Here, I would like to see your response. So maybe you can, if you think they are independent, please just click on yes. What can I do? Yeah, you can just say yes. And if you think they are not independent, please say no. Okay. George said they are dependent. No. Okay, wonderful. Then I will stop. And right here, you can see another example again. So Y is a quadratic function of X. They are uncorrelated, but clearly they are dependent. And then whenever you do regression, linear regression or nonlinear regression, by construction, the regressor is uncorrelated from the regression residual, but they are not necessarily independent, as you can see from this illustration, which we will see in half a minute. So right here, you can see the shape of different probability density functions. This is the Gaussian distribution. All variables have unit variance and zero mean. So this is the Gaussian one, this is Laplace distribution, and this is the uniform distribution. Right here, for the Laplace distribution, you can see the probability distribute the density, the value of the density function is very high for values very close to zero for small values. And also as a consequence, because we have the same variance for the three variables, right here the distribution would be higher. That's why we say it's a fat-tailed distribution. This is Gaussian uniform. And right here you can see the data points drawn from the distribution. You can see how they look like. Okay, now let's try to go from correlation to asymmetry between two variables in the linear case. First of all, let me just generate the data this way. I first generate x, and then I generate y from x by making use of this process. Y is the linear, y is just a coefficient times x plus independent noise e. In other words, according to this process, x causes y, right? And then the first row shows the Gaussian case, where x and e are both Gaussian, and finally, x and y are jointly Gaussian. So this is the scatter plot. And now let's try to explain the effect of y with the cause x by linear regression. So we regress y on x. We have the residual, and the residual is uncorrelated from x, and also they are independent. Why? Because we just recover the original noise term, right? And then we regress x and y, the different direction. And we find the residual. Again, they are uncorrelated. And again, they are also independent because in the joint Gaussian case, as long as they are uncorrelated, they are independent, right? That's why the joint Gaussian distribution is very attractive in many cases, because in this case, uncorrelated or zero correlation is equivalent to independence, statistical independence. In the second case, we have non-Gaussian distribution, and in particular, both x, the cause, and e, the error, follow the uniform distribution. And here you can see the scatter plot of x and y. Now we do linear regression. We regress effect y on the cause x. We recover e. They are independent. So the error term would be independent from x. Now we do the same thing in a different direction. We regress x, the cause, on the effect y with linear regression. Now we can see, again, they are uncorrelated by construction. They are uncorrelated. However, they are clearly dependent, right? So for the wrong direction, the regression residual would be dependent on the hypothetical cause of the predictor, as you can see from here. That's why we can discover causal direction between x, y in the linear non-Gaussian case. Because for a wrong causal model, the residual will not be independent from the predictor. However, this is not the case if the data are jointly Gaussian, as you can see from this row. Right here, you can see the Super-Gaussian case. Again, I generate the y from x this way. However, x and e are both sparse or both fat-tailed. I use the Laplace distributions for x and e. Here you can see the scatter plot of x and e, and this is the scatter plot of x and y right here. And if you do regression, if you regress y on x, you can see you can recover the noise, right? And they are independent. However, if you regress x and y, as you can see from here, the residual, although uncorrelated from y, is clearly dependent on y because the distribution of this variable given the other variable would be sensitive to the value of the second variable. They are not independent. Right here, you can see this is the regression line. It's not here. Why? Because we have a lot of data points here, right? That's why this regression line cannot just go through those data points. It's something between this cluster and this cluster. Okay, so basically you can see intuitively, we know that in the linear non-Gaussian case, we can discover the right causal direction. And if you find the causal structure with the right causal direction, then you can estimate the causal parameters. Because if you have the structure and the data, you can just use the regression to find the causal coefficients. So more generally, we have this linear non-Gaussian acyclic causal model, in which each variable is a linear function of its parents or direct causes and some independent noise. And in matrix form, we have this. This x is a vector of all variables. X is b times x plus e. And right here, b is called causal adjacency matrix or weighted causal adjacency matrix. So b has a bij as entries. And we assume the disturbances or noise terms or errors are non-Gaussian, or at most one of them is Gaussian. And clearly, we assume they are mutually independent, as we just saw from the assumptions for functional causal models. Probably there are questions. Let me have a look. Okay, I got a question here, so let's just pause for a moment. What's the feature of non-Gaussian distributions that makes them suitable for this inference? Would it work for general elliptic distribution as well? Okay, good. So as long as the distribution, the non-Gaussian, is fine. Later you can see why. Okay, I will give you something probably in 2 or 3 minutes. You will see why and how the Gaussian distribution is so different from the non-Gaussian distributions. And you can see what features in the non-Gaussian distribution can be used to determine some essential information uniquely. Okay, just wait a second. Okay, right here at the bottom, you can see we have a set of equations or structured equation models. Remember definition, right? It's a structured equation model because for each equation, the variable on the left-hand side of the equation is the effect, and those on the right-hand side of the equation are the parents of that variable. And equivalently, we can represent the system with graphical models. Right here, we know all x2 is a direct cause of x3 with the parameter or causal coefficient 0.5. And usually, we don't explicitly give the noise term. Here, I just give the noise term in order to better understand the relationship between the noise terms and the observed variables. Now, the problem is how we can estimate this causal model from data, from observational data for xi's observed variables. In other words, we want to find the B matrix, because if I have the B matrix, that you will see that if I have the B matrix, then I have either this graphical representation or this set of equations. In other words, we have the causal information. And we can make use of a statistical technique known as independent component analysis, ICA. So right here, this is how ICA works. We have a set of observed variables xi's, x1 to xm. They are assumed to be linear mixtures of some underlying unobserved independent variables si's. So they are linear mixtures. And this part, everything here, right, is not observable. To recover this hidden system or information of this hidden mixing procedure, we just apply another linear transformation, W. We tune the parameters to make the outputs yi's independent or as independent as possible. And then, under some assumptions, we know that the estimated variables are just the estimator of the originally independent variables, si's. So basically, we just estimate those variables by making use of yi's, the outputs of the linear transformation or the demixing procedure. And we know that this is one way to invert the system in some sense. So this is the linear mixing procedure. Observed variables are linear mixtures of the hidden independent variables. And right here, we apply linear transformation to x observed variables, and we find the independent components as components of y. So under two assumptions, we can just recover the originally independent variable si's just with some trivial indeterminacies. What assumptions do we need? The first one is that at most one of the independent variables si's is Gaussian, at most one. later you will see why we have to make this assumption. The second one says that the number of sources is either smaller than or equal to the number of observed variable sensors. So right here, n is not larger than m. Otherwise, it's called overcomplete. It's more difficult, much more difficult, because you have more variables in the hidden part, but you only have a smaller number of variables that you can observe. Recovering this system is not very easy. But now we assume that's not the case. So under those two assumptions, we can just estimate this A matrix up to the scale and the permutation indeterminacies. What does it mean? First of all, we cannot recover the scale of A because we can always exchange some factor between S and A. It's trivial. In other words, if you just basically exchange some factor between A and S, you will not change the independence between SIs, the independent variables. And the second, we cannot determine the permutation, right? We cannot recover the permutation of SIs because no matter how you permute them, they are always independent. Okay, so this is ICA. And right here, you can see the difference between Gaussian distribution and non-Gaussian distributions. This is ICA procedure. We have this set of set of observed variables, xi's. We have linear transformation. We want to make them independent, the outputs independent, right? And usually, ICA procedure has two steps. First, we do something like whitening. We want to make the outputs uncorrelated from each other, and at the same time, we want each component to have a unit variance. So this is called whitening. After this, we just need to find a rotation or orthogonal transformation to further make the output independent. So the first step is the standard. You can just do EVD or SVD decomposition, and then you can white the data. Now let's try to find a rotation or orthogonal transformation to make the components of Y independent. In the first case, variables are Gaussian. Now you can see no matter how you rotate them, right? No matter how you apply rotation transformation to the variables, they are always independent. Meaning that you cannot recover the underlying mixing, the information of the underlying mixing procedure. However, in the other three cases, we can recover the essential information. In the first case, you can see, although they are uncorrelated, clearly they are not independent. To make them independent, to make the rotated variables independent, we have to do something like this. Or you can go further, right? Then you can just change the sign, or you can just change the order of the two variables, but they are independent. And you have to rotate them this way, either this way or that way. But in any case, you can recover the essential property of the mixing procedure. And in the second case, right here we have a scatter plot, right? A way to visualize the joint distribution of the data of the variables. And in the second case, basically originally the underlying independent variables are uniformly distributed. So you have to rotate the variable this way. And in the third case, one independent variable is Gaussian, is actually uniform, and the other is Gaussian, I think. Right here, you have to rotate the variables this way, then you can make them independent. Now you can see the difference between Gaussian and non-Gaussian distributions, right? The Gaussian distributions is just, the Gaussian distribution is very simple. We just need to specify the mean and the variance or the covariance if you have multiple joint Gaussian distribution. It's so simple, it's so smooth that no matter how you rotate the variables, it's just the same thing, as you can see from this illustration. But in the non-Gaussian case, you can really find a relatively unique way to make them independent. If you further rotate them, they will not be independent. Okay, so this is why. And now you can see a demo of the ICA procedure. Right here, we have two observed variables, x1, x2, and on the right, we have the scatter plot as a way to illustrate or to show the joint distribution of the variables. And then we do the first procedure, we do whitening. Now they are uncorrelated, and each of them has a unit variance. You may wonder that, right? Note that here we have a lot of data points here. That's why although the shape is very strange, actually this variable and that variable are uncorrelated. Although you can see a trend. Okay, then we go further. First step, second step, and then now you can see finally we can find independent components from the two variables. And now you can see they are very simple and they are structured, right? And they are independent. This is how, okay. This is how ICA works. Let's just pause. Question, is it always possible to make the transformed variables yi independent between each other for general distribution if y is restricted to a linear transformation y equals w times x? So basically the question says that, can we always make the outputs yi's with a linear transformation independent from each other? So the answer is no, clearly no. As you just said, right? In many cases, suppose you just have uniform distribution within a circle, right? Within a circle, uniform distribution. Now you can see no matter how you apply linear transformation, the variables cannot be independent. The distribution of one variable will be sensitive to the value of the other variable. So the answer is no. That's why in some cases, we have to make use of nonlinear ICA or some nonlinear methods to find disentangled representations. Is that the answer to your question? Okay, great, thank you. So now we just saw how we can do ICA, and then let's see how we can solve the problem of causal discovery by making use of the ICA procedure. Very quickly. So in the first row, you can see the linear non-Gaussian model in the matrix form x equals bx plus e. In other words, e, error term, independent error terms, right, can be written as a linear transformation of x, linear transformation. And there, this is the ICA demixing procedure. We have W. Now you can see, oh, E has independent components, Y has independent components. I minus B, the linear transformation, W, linear transformation. That's why this is the mixing procedure of ICA and this causal model are related. Now the problem is how we can make use of this connection to find the matrix B, because B contains the causal information between the variables xi's. So first, how can we find W? We can do so with ICA, right? We just saw that. Second question, how can we see B matrix from W? How can we analyze the W matrix to obtain B? And this is interesting, and I'm going to give examples to illustrate that. So suppose this is W. Now we just need to do three things to find the B matrix. First, we permute the rows of this matrix to make all diagonal entries non-zero. Right here, you can see, oh, I have to permute the matrix, this matrix this way, or the rows of the matrix this way, to make sure all diagonal entries are non-zero. And the second is to divide each row by the diagonal entry. And then you can see after that, all entries on the diagonal are just one. And then B, the ultimate, the causal adjacency matrix is just the identity matrix minus this matrix, as you can see from here. And then diagonal entries will be zero. Remember that, oh, I haven't really talked about that. So the B matrix, causal adjacency matrix, right, has zero values on the diagonal. Why? Because this represents self-inference or self-loop. This is the inference of x1 on x1, right? That's why we don't assume there are no self-loop, because this kind of information cannot be recovered from data. So it's just zero. And then we have this causal structure. Accordingly, we have this causal graphical representation. So you can see the first one says, oh, x1 is not influenced by any observed variables. The second row says that x2 is influenced by x1 with parameter minus 0.5. And the third row says the third variable is influenced by 1 and 2 with parameters minus 0.3 and 0.2 and so on. So now with this example, you can see how we can solve the problem. In particular, because the causal graph is assumed to be acyclic, right here, the solution is unique. So we can just recover the underlying DAG uniquely from data asymptotically if you have enough data, right? Otherwise, you may have random error and you can make wrong conclusions. And this is a really big step because previously when we made use of conditional independent relations, we could only end up with a equivalence class. We cannot really find a unique DAG, but now by making use of additional assumptions on the causal mechanisms, including the non-Gaussian distribution, we can just recover the underlying DAG uniquely. Okay, in a minute we are going to have a break, but now let me just finish this part because it's closely connected. Some of you may wonder whether it's really reasonable to assume the variables are non-Gaussian, right? We use Gaussian distributions almost everywhere, partly because the form of the probability density function is very, very simple, partly because of central limit theorem, right? If you have the sum of independent variables and allow the number of independent variables to go to infinity, then you have a Gaussian distribution under very mild assumptions. And partly is because of the very nice property of the Gaussian distribution. If the joint distribution is Gaussian, then conditional distribution is Gaussian, marginal distribution is Gaussian. However, another theorem is actually complementary to central limit theorem, but it was kind of largely overlooked in the literature. It's a Cramer decomposition theorem. It says the following thing. If the sum of any finite independent variables is Gaussian, then each of those variables must be Gaussian. If the sum of, say, 10 independent variables is Gaussian, then all those 10 variables must be Gaussian. In other words, the Gaussian variables are closed. They are in the closed system. If you put anything non-Gaussian there and allow this non-Gaussian variable to interact with other variables, then finally all variables will be non-Gaussian, right? So in this sense, Gaussian distribution is really special. And you can also say that if we have linear world, if the relationships are linear, then the distribution shouldn't be Gaussian, right? Of course, the practical issue is how non-Gaussian they are, how many data points we have to make use of to really discover and make use of the non-Gaussianity of the distribution. Here you can see an application of this method, some extended, some modified version of this method to analyze the Hong Kong stock market. So basically here you can see 14 major companies in Hong Kong, and we analyze the daily returns, right? If you have daily return, the resolution is very low, and the causal relation would seem to be instantaneous without a time delay. So right here, yeah, I'm going to skip this, but basically the information is largely consistent with the background information or domain knowledge in the stock market. So let's take a break, and we'll resume in 7 minutes. Thank you. And if you have questions, please. Okay, here, yeah, so you can just go and come back in 7 minutes. And now I want to answer the questions. If you have any, one question that follows, maybe I missed some part. What are the values that we get for the edges? How can we interpret them? Okay, those values in the linear case, they are causal coefficients to indicate the causal strengths. Let me just go back to the graphical representation. Right here, you can see on the left, we have the equation. This equation says that x2 causes x3 with a coefficient 0.5. The larger this parameter, the heavier the causal influence would be, right? So this is just a causal strength. And this is how you can interpret those values. In the linear case, in nonlinear cases, we don't have such values, and we have to develop method to measure causal strengths. In the linear case, very simple. If you standardize the variables to make them have univariance, then this value will immediately give you, will tell you how strong this causal inference is. Okay, is that the answer to your question? Okay, great, thank you. So if you have further questions, please just leave them in the chat window. Oh, now maybe this question will be answered later. In any case, can it be that reasonable extra assumptions, e.g., in linear non-Gaussian and nonlinear F, the causality reversed? Oh, I'm not sure about what you want to say. Extra assumptions. Yeah. So basically, you will see that in some time, even in nonlinear cases, we can do the same thing. We can find the right causal direction. Means that if you for the reverse direction, right? For the reverse direction, the independent noise condition will not hold true. That these different methods lead to different errors. Now I see. No. This is because later you see this. Even for the very general one, the last one, with double nonlinear transformations, we can prove that only one direction admits independent error term. And if this is the case, then clearly for other more restrictive model assumptions, like linear non-Gaussian models, clearly we have identifiability of the causal direction, right? Because even with the general model, you cannot find an independent error term. Then, of course, with more restrictive assumptions, you cannot find the independent error term. So, okay, great, thank you. Rodrigo, how are you? How is everything going?
Everything is great, Kun. Hi.
Oh, great. Sorry, yesterday I was kind of sleepy, and today, now it's 3 a.m. That's why I'm a little bit sleepy. Yeah.
Yes, I was wondering also in which time zone you're located, and well, 3 a.m. is really late. So thank you very much that you can make it so at this time of the day, and yeah, so I think we are covering a lot of material that's very interesting for everyone.
Nice. I'll try to make it complete because it's a tutorial, not a talk, not a invited talk keynote, right? So I just want to cover all those things that are might be relevant and might be interesting to some of the audience. But yeah, it's very dense. So just to all of you, if you want to see more detail, I think you have to read the slides afterwards. And I provide the references. So if you really want to see detail, just find the papers or books. Just have a look. And if you have questions later, you can just email me. Okay, let me get some more water. I will come back in half a minute.
All right.
Okay, should we continue?
We can continue.
Okay, so just now you saw how we can estimate linear non-Gaussian models from data. And the solution, if the model assumption holds true, then you have a unique solution, meaning that you have a unique structure, including the parameters, the causal coefficients from data. And right here, now let's try to go further to make it more general. Here you can see the scatter plot of x, y, where y is the nonlinear function of x plus e. This nonlinear function is very simple. It's just kind of piecewise linear. I have this, and then I have that linear function. I have independent noise added to the function. So here, if you try to, if you regress y on x clearly, you can find the independent error term because you just recover this true model, causal model from data. However, if you switch them, x, y, and do regression, if you regress x on y, now you can see the error distribution will be sensitive to the value of y, as you can see from here, right? So this means, generally speaking, even in the nonlinear case, with the wrong causal direction, with the wrong direction, you cannot find the independent error term. Okay, so this is basically something similar to what you observed in the linear non-Gaussian case. More generally, let's have a look at the post-nonlinear causal model. So when we develop this model, we believe that the model itself should be very, very general, so that it can be used to approximate the true generating process. And second of all, we have to guarantee that the causal direction is identifiable. Otherwise, it's not meaningful to make use of the model for causal discovery. So we believe that 3 effects should be considered in the model. So here we have nonlinear effect of the causes, we have noise, and in many cases, we have sensor or measurement distortion. If you want to measure something, right, you have to use instrument, and this will introduce some error. And this is the typical issue, or this is the typical case for biological data and for data in social sciences. And later, so you can see some examples. And this model right now, this is called the post-nonlinear model. This is very general. Even if the noise is not additive, but multiplicative right here, you can see it's a special case. Right? This is nonlinear function, this is a function of f, and this is noise. They are independent, and basically this is just another way to put the multiplicative noise model. So the model is very general. Can we make use of this model to discover causal direction? The answer is yes. Now here you can see some evidence, empirical results. We are given data sets. We are given the data pairs for x1 and x2. And right here you can see the scatter plot. If you assume x1 causes x2 and fit the model on the data, you find the nonlinear transformations and you recover the noise term. In this case, they are independent. And then if you switch them, if you assume x2 causes x1 and fit the model, then you can see the additive noise is not independent from the hypothetical cause, which is x2. Now we say, oh, according to this model, x1 causes x2. Actually, x1 and x2 are the altitude and temperature, yearly mean temperature of more than 300 cities in Germany. So altitude should be a cause of temperature, not the other way around. This is the second one. So here, again, you can see, according to this model, x1 causes x2, because for this direction, we can find the independent error term according to this model. But for the other direction, we cannot. And here, x1 and x2 are the altitude and precipitation, respectively, for the cities. Okay, so you can really find the causal direction, even if the causal model is rather complicated, right? It involves 2 functions, 2 nonlinear functions. Okay, now I'm going to give some theoretical guarantee. How can we trust the result, right? We just prove the identifiability of the causal direction in the 2-variable case by making use of the proof of contradiction. So given data, suppose the ground truth is x1 causes x2, right? Now we assume that the other direction can also satisfy the post-nonlinear model, that model. And then for the same distribution, right, we assume both of them hold true. we'll find the constraint, which is actually a differential equation. And then we can solve the equation. And finally, you can see there are only 5 solutions. In other words, in only those 5 situations, we have the symmetric relationship between the cause and the effect, right? Means that even for the wrong direction, we can find the independent error term. And those cases are actually very specific. The first one is the linear Gaussian case. The function is linear and distribution is Gaussian. So in this case, we know that we cannot find the causal direction between 2 variables because they are symmetric. Their correlation is equivalent to independence. And all of them are very specific. You have to tune the nonlinear functions and distributions very carefully so that one of them is true. So in other words, generally speaking, causal direction is identifiable, even if data were generated according to this very general model. And since linear model and nonlinear additive non-model are special cases, this result also applies to the 2 simpler cases. So in other words, generally speaking, causal direction is identifiable from observational data, even if we have this very general model to generate the data. Okay. Any questions? So far, we just saw how we can make use of linear non-Gaussian causal model and nonlinear causal model to discover causal information. In particular, here, I focus on how to identify the causal direction, because this is the missing part for the previous methods based on conditional independent relations, right? With those methods, you cannot find the direction between 2 variables. Sometimes you can find the direction because of this structure, right? But generally speaking, you cannot solve the problem in the general case. Now we can, because for any 2 variables, we can solve the problem. Then no matter how many variables you have, in theory, you can solve the problem. And now let's have a quick look at some extensions of the functional causal models. First problem is very important, very practical. It's a causality time series. So we just focused on a very hard problem, which is how to find the causal information from ID data. What if we have time series? Right? How can we discover causal information from time series? So I just want to give a rather complete introduction to the problem. So here you can see this is traditional work, very classical work, Grandier causal analysis. Right here, Grandier himself said that Grandier causality is not necessarily true causality. That's true. Actually, only under very restrictive assumptions, Grandier causality is true causality. Those assumptions include that there are no confounder and that you have the right resolution for the data. So if you have low resolution of the data compared to the original causal frequency, then you cannot recover the true causality by Grandier causal analysis. Okay, and then you can just view this problem, causal discovery from time series, as a special case of causal discovery from ID data. What does that mean? It means that we can just apply constraint-based methods combined with the temporal constraints, temporal precedence information. Causes happen before the effects, or they can happen at the same time if you have low resolution, but causes cannot happen after the effects. So this is the method used in this paper. And also you can apply the functional causal model like linear non-Gaussian model to the data. And also further, you can apply, you can benefit from temporal constraints, right? So in other words, you can just consider causal discovery from time series as a special case of causal discovery from ID data. And then you can also consider both the time-delayed causal relations and instantaneous causal relations. Right here, as you can see this paper. And you can discover true causal relations at the original causal frequency from low resolution data. Here by low resolution data, I mean you can have subsampled data or temporally aggregated data. Later you'll see the definition. And furthermore, you can recover true causality from partially observed time series. And here you can just see the references. Now I'm going to show two pictures, two slides. One of them is on the connection between granular causality and constraint-based methods for causal discovery. So granular causality relies on two principles. The first one says that future cannot cause past. The second one says there are no redundant information. So basically says that there are no deterministic relationship. Cause contains unique information about the effect. Then, according to Granger in this 1980 paper, we say X causes Y if this conditional distribution given the complete information set is different from the conditional distribution of Y given the information set without knowing X for this moment, right? So what does it mean? If this inequality holds, we say YT plus 1 is conditionally dependent on X given the remaining information, right? So this is just one particular way to find the causality based on conditional independence relations. And furthermore, you know, our causal direction can only go from the past to the future. That's why you can immediately recover the whole model by making use of this condition, this conditional independence condition. In practice, sometimes we have causality mean or linear granular causality. To do so, we can use something like vector autoregression model, right, to capture the causal relations. Okay, so this is how granular causality or granular causal analysis is connected to the conditional independence-based method for causal discovery. And right here, you can see what I mean by the two schemes of temporal of deriving low-resolution data from high-frequency data. So in many cases, causal relations can happen very, very quickly, right? Like in stock market, if company A causes company B, then the causal inference will take place within 1 minute and 20 seconds. Usually this is the case, but very often time we just analyze low-resolution data set, daily returns, right? So the first scheme is called subsampling. Right here, we can see we have the original high-frequency time series, and then we only keep one of them, right? This one, x1, and then xk plus 1 and x2k plus 1. So we just keep one of them every every k consecutive data points. We only keep one. This is called subsampling. And right here, you can see the graphical illustration of this procedure. We have the original causal process time series, and then we cannot observe the information in between, right? Between this observed value and that observed value. And now you can see, not surprisingly, if the k downsampling factor is very large, then you have a lot of missing information. And finally, causal information tend to disappear, right? So suppose X, this guy calls that guy, and every time, right, you have the causal relationship, and suppose you just miss a lot of values in between, and finally, the first one and the last one will seem to be independent. This is the subsampling, and the second one is the aggregation, temporal aggregation. So you just take the sum of the k consecutive data points. And this is in practice, we very often time we have this issue, right? The daily return, stock return, is actually the sum of the short-term log returns. And in this case, it's very nice to see the following thing. As you increase the aggregation factor k, the causal relations are still there, right? As you can see from this equation, if you compare the original causal process represented by this vector autoregression model and this model, you can see, oh, I still have the same A. However, I do not have time delay. So time delayed causal relations will look instantaneous. So that's and also at the same time, we cannot recover the information of self-loop. And if you have finite k, we can recover the original causal information or true causal information from data. And if you want to make use of the method, or if you want to go further in this line of research, you can have a look at those papers. Okay. To give examples, for instance, GDP is aggregated data. fMRI signals are usually aggregated data. Stock returns are aggregated data. Temperature data are just subsample data. Okay. And now let's have a look at how we can deal with the confounders. So first, suppose we don't care about the confounder, we just care about the causal relations between observed variables, right? So FCI provides a way to recover some information, but it's not really complete, because whenever it's possible to have a confounder, you have to indicate that. So right here, by making use of overcomplete ICA, we can recover the structure of the observed variables, even if they are confounders. And under some further assumptions, as you can see from this paper, we can even uniquely identify the causal parameters, causal coefficients, represented by A3 here. Here, we have to use overcomplete ICA because, as you can see from this example, we observe two variables, but actually they are effects of three independent variables: this noise term, and this confounder. That's why it's called overcomplete ICA. Okay, so we can say something, but right here we have no idea about the relationships among the latent variables. However, in many cases, the measured variables, like image pixels, are just reflections of the underlying meaningful causal variables, hidden variables, which are causally related. And then, if you want to understand the system, you want to discover the hidden variables as well as their relationships. How can we solve the problem? And this problem is sometimes known as hidden causal representation learning, or discovery of hidden causal representations. In the linear Gaussian case, one can make use of the tetrad condition to solve the problem, as you can see from this very nice paper. And you can go further. In the linear non-Gaussian case, we just need to make rather weak assumptions regarding the structure. And we can go further. For instance, if you make use of the triad condition given in this paper, in this case, you can recover not only this structure, but also the causal structure, including directions for the latent variables. So you can recover not only where the latent variables are, but also how the latent variables are causally related uniquely. Of course, here we are considering linear models. And so far, I don't think there's any kind of convincing work on how to discover the hidden variables and their causal relations in nonlinear cases. This problem is very important, but you have to do the work. Last issue I want to mention as the extension of causal analysis based on functional causal models is how to deal with measurement error. In many cases, we have measurement error, right? If you use the instrument to measure something, this process can introduce error. And in some cases, we don't even have a very good way to measure the variable. For instance, if you want to see the regional safety, right, of a particular country, a particular area, what can you do, right? You have to make use of some other variable, like the number of crimes per day or number of crimes per month as a surrogate for that variable. Then inevitably, you are going to have measurement error. The measurement error is the error in the observed variable relative to the underlying hidden variable you are really interested in. Here you can see a graphical representation. So here xi tilde are the hidden true variables we want to analyze. And unfortunately, we have measurement error, right? We observe xi's, they contain measurement errors. First of all, the conditional independent relation between the observed variables can be very different from the true variables, from those relationships between the true variables. That means we have to do some adaptation to recover the true causal structure for the noise-free variables. And even if you apply functional causal model-based method, you suffer from the same problem because even if this guy calls that guy, so x2 tilde calls x1, now because of measurement error, even if you consider relationship between x2 and x1, right, in the right direction, you don't have independent error term. But we just studied this problem And the conclusion is as follows. Under rather mild assumptions, we can still recover the essential information of the underlying true graph over the measurement error-free variables. So, and we propose some method to solve the problem. Again, we assume linearity. If you consider nonlinear model of the problem, you can do something. And that's very important because we often have nonlinear relationships in practice. Okay, to summarize, right here, first of all, we know that conditional independent-based method or constraint-based method often end up with equivalence classes. So we want to go beyond that to recover the underlying DAG uniquely. How can we do so? We can just make use of some rather mild or strong assumptions also on the causal mechanisms. So if you assume the data is a linear non-Gaussian, then we can recover the underlying model uniquely. And if you know that the procedure is nonlinear, then usually we can recover the underlying causal DAG uniquely again. And in practice, there are so many issues to address, right? And just now, you just saw how we can deal with hidden variables and their causal relations and measurement error, and how you can discover causal information from time series. Of course, there are so many open problems in causality, especially in causal discovery. So you can easily find some problem to work on. Okay, so let's take a 20-second break. Is there any question? I know it's very fast, but maybe you want to have a look at the slides later. And in particular, if you are interested in a specific topic, just find a reference.
And we have also gathered some questions that we can answer at the end.
Oh, or maybe if you already have a question, can we just answer the question right now?
We can answer questions right now. Yes, sure. Let me.
Yeah, because otherwise, if you get probably there, yeah, some of them will forget the question.
So connected to now, so the presentation on Granger causality. So we discussed causality in time series, but what about causality for sequences? For example, event data or even NLP. Can the same techniques be applied?
Sorry, I missed the last sentence.
Yes, so if the same techniques, for example, Granger causality or the general techniques that we have seen today and yesterday, can be applied for sequences, not only time series, for example, event data or NLP.
Yeah, yes, a very good one. First of all, I think, yeah, you can, because I just talked about the general principles. And furthermore, if you have other kind of data, sequential data or structured data, you can go further. You can make use of the structural information in the data. So answer is, first of all, yes. Second of all, probably you can go further by making use of the specific property of the data you have.
Great. And also another question is that there have been recently approaches using deep learning for causal discovery, for example, from the Benjos group. We have not discussed them here. What are your thoughts on them?
Okay, that's a very good question. So you can always design methods to solve the problem, but the most important thing is to really find a principle based on which you can solve the problem, right? For instance, right here, for causal discovery from non-stationary or heterogeneous data, I presented the basic work based on conditional independent relations. Okay, let me quickly go back. And Benjo and his group did something, right? It's a method, but basically they use something like a quick adaptation as a criterion, right, to find a causal representation. Actually, here we just use the conditional independence, and as you can see from this result, from this framework, conditional independence is a principled way to do causal discovery. And of course, in practice, you can use some other criteria to achieve something similar, right? They are related. And that's why I didn't talk about that specific method, because we have to wait to see whether the principle is really a good one for causal discovery from non-stationary or from data with distribution shift. So, but if you are interested, we can have a discussion later. Okay.
Mm-hmm. Mm-hmm. And another question is on if it is possible to do causality in general without the do calculus.
Okay. We use the do calculus to use causality, right? No, there are different interpretations of the results. First, classical way to find the causality is to use interventions, right? We intervene on something and then see the effect, then we can find the causality. So from this perspective, yes, with the do calculus, by which I suppose you mean interventions, then we can find the causality. Second, right now I'm talking about the causal discovery, in which we just make use of observational data without any intervention, and we aim to discover true causal information. And third, if you know the causal model, in particular, if you have the causal structure and observational data, then you can just identify causal effects, which involve the causal effects involves the do calculus. You will see this in probably 3 or 4 minutes. So basically, I just try to give my answers according to my understanding of the question. If it's not clear, or if it's not what you mean, maybe you can just go further. You can just ask questions. Thank you.
Then another question is that there are many names for the field in publications, for example, causality, causal discovery, causal inference, causal structures. Where do you draw the difference? Are there any differences?
Very good one, very good one. So I tried to, you can see, I always distinguish between those terms. Here by causality, I mean, basically causality is just a field, right? As long as you care about the causality, you say the causality research. And then I use the term causal discovery. By causal discovery, I mean finding causal information like a causal structure or causal model from non-experimental or observational data. So you don't do interventions, you want to discover causal information. This task is known as causal discovery. The third one is a causal inference or identification of causal effects. So right here, you will see this. I will define this problem in a few minutes. Basically, this problem is very different from causal discovery because causal inference or identification of causal effects assumes that we have a causal structure and then qualitative causal structure, and then you want to estimate the quantitative strength. You want to see how X influences Y, right? You want to see whether this influence is really significant and so on, or very heavy and so on. So they are very different. And structure learning, so causal structure learning is the same as the causal discovery because you want to discover causal information. And in contrast, we also have Bayesian network learning, right? Bayesian network learning is also a kind of very huge, it also has a very huge community. Bayesian network learning is different from causal discovery because if you want to learn a Bayesian network, you don't care about whether this Bayesian network is really causal, right? For instance, if you have two variables which are dependent, then you don't care about the direction if you just want to end up with a Bayesian network. However, if you care about causality, you have to find a direction. You have to make sure this direction is causal, right? So, however, Bayesian network you learn that you can learn from data is related to causal representation. Why? This is why just now you can see that with the conditional independent Bayesian method, we just end up with the equivalence class in which usually we don't have a unique DAG, right? This is because you can, if you just learn Bayesian network from data, then you can always convert the learned Bayesian network to an equivalence class, and then you can trust it. By trusted, I mean the following thing. If the age is directed, you can trust that, oh, this guy is the cause of that guy. If the age is undirected, undirected, right? Then you say, oh, I don't know the causal direction. But if you just view that as a Bayesian network, the direction can go either way. Now, from the causal perspective, as a causal representation, you cannot do so. If you cannot determine it, you just say, I don't know, represented by an undirected edge. So I hope this just clarifies the differences between different concepts.
So another question, so more general one, is if there are success stories in machine learning using causal methods.
Yeah. Oh, let's see whether we have time for that. Yes, that's true. Clearly, in many cases, we care about the causality, even if we want to do machine learning. I will try to give examples and some tasks at the end of the talk. Okay. And in case you don't get the answer you want, please email me or just stay here after the tutorial. Okay. Anything else?
Yeah, so last one is that the causal inference and reinforcement learning, they seem to have similar objectives. Where do you see the differences between both fields? Where do they complement each other?
Which fields?
Reinforcement learning and causal inference.
I see. Reinforcement learning and causal inference. That's a very good one. First of all, if you do reinforcement learning, most of the time, right, you have causal information. By default, you make use of causal information, right? You do this, you know that our action will change the state. Action will lead to some reward, and so on. So from this perspective, a lot of people in reinforcement learning believe they are making use of causal information, right? However, at the same time, probably in some cases, you need to make use of the properties of causal system more rigorously. So in other words, even if you do reinforcement learning, it is possible that you can formalize the intuition you use to solve the problem by making use of concepts and methods in causality. And this way, maybe you can solve complex problems in an easy way. For instance, probably you can deal with the confounders or changing environments or other problems in a more principled manner. Okay.
Great.
Yeah, in case you are not happy with the answers, please indicate that. Okay, thank you. Now we don't have much time, so let's go to next part. Because
yes.
some questions are related to next part. So last part. Come on. Yeah, I'm waiting. Okay. So in this part, you see how we can identify causal effects. This is one of the questions I just received. So you can see what we mean by identifiability of causal effects, and you can see how we can estimate them very briefly. And also you can see the definition of propensity score and why it's useful for identification of causal effects or causal inference. And then you see a very quick look at the relationship between causality and machine learning. If time permits, I will share some general thoughts, and also we'll have a look at causal ways of doing domain adaptation. Remember, we have 3 questions to answer in AI. The first one is sometimes called conditioning. The second one is sometimes called manipulation, and the last one is counterfactual. Clearly, for the last 2, we care about the causal relationship. And the second one is what I'm going to talk about right now. We want to see the effect of interventions. So it's about identification of causal effects. So here you can see I have a probability distribution of recovery, this variable, given intervention on treatment. So this is known as the causal effect of treatment on recovery. Okay, how can we find it? So the golden standard is to make use of randomized controlled experiments. So here, in this case, you have 2 groups. One is a control group, the other is a experiment group or treatment group. And then you have to make sure that all the other relevant features either have the same value across two groups, or you have to make sure that those features are completely random following the same distribution across the two groups. And then, given that all the other features either have the same value or the same distribution, if you observe a difference in recovery, then this difference must be caused by treatment. In other words, you are sure there are the causal relation from treatment to recovery, and also you can estimate it from data. You can estimate how strong it is from data. However, these kind of experiments are very expensive. And in many cases, it's not possible to do the experiments. For instance, in social sciences, right, you cannot force people to divorce, right? So many things are prohibited. What can we do? However, we can just collect data. We can observe data, right? And here you can see an example regarding how we can solve the problem. Remember this example, Simpson paradox. We have a common cause, stone size. We want to see the effect of treatment on recovery. So if you care about this, if you look at this row right here, essentially this row is implied by the dependence pattern, or in particular conditional distribution of recovery given treatment. How can you calculate the conditional distribution? Basically, you make use of this equation, right? Right here, you have distribution. You have to marginalize out S, stone size, and you have to make use of the conditional distribution of stone size given treatment right here. This is just an application of the chain rule and the sum rule. And if you want to find the causal effect represented by the probability distribution of recovery given treatment, given intervention on treatment, we have to do this. Remember the definition of intervention. You have to cut this guy off, because when you do intervention, you don't make use of the original mechanism for this variable. You just set the value to some specific one, say A or B, right? In other words, when you do that, when you do intervention, the conditional probability distribution of stone size given treatment would be the marginal distribution of stone size without condition on treatment, because after you do intervention, S and T, stone size and treatment are independent. Now, this is the equation you can make use of to find the causal effect of treatment on recovery. Okay, and those two equations just show the difference between conditioning and manipulating. You basically do manipulation or intervention on this variable treatment. Now let me try to give a graphical illustration on the difference. Here, right here, I have patients with small stones. Those patients receive treatment A, those receive treatment B, and the y-axis is the recovery success rate or recovery rate. And the size of the circle indicates how many people with stone size receive different treatments. So a small number of them receive the A, and a large number of them receive the B. And the same thing happened to patients with large stones. A lot of them receive A, and only a small number receive the B. Now, if you do conditioning, essentially you just use this way. You just marginalize out S according to this equation. You just average the success rate with this weight. And this weight is sensitive to treatment. And right here you can see, oh, here I have a lot of people. That's why the average, the value would be close to this value. And for B, here I have a lot of people. That's why the average, the value would be close to this value. And now you can see, according to the conditional distribution or the mean of success rate, or B seems to be better, right? But this makes no sense if you want to give a recommendation, because it's not causal. In contrast, if you consider this conditional distribution R given intervention on T, this is just a way to measure causal effects. Now you can see we have PS as a weight when you integrate out S, or when you sum over S. In other words, when you take the average of this value and that value, and when you take the average of this value and that value, you just use the same weight. This weight is not sensitive to treatment anymore. And then you can see, oh, you will see the same trend. Now I see, according to this measure, A is better than B, right? So this is the difference between conditioning and manipulating. Okay, formally, what do I mean by identifiability of causal effects? First of all, we know this is a representation of a causal effect distribution Y given intervention X to X. And then remember the setting. We have two things. First of all, we have a structure. Structure is given. Second, we have data. We have data for only a subset of the variables. Right here in this example, suppose we only observe treatment and recovery. Suppose this guy is hidden. Now you can see we are given the structure. We know, oh, there is a common cause which is not observable, and we have data for those two variables. Now, the question of whether the causal effect represented by this guy is identifiable is defined this way. We want to see whether two different causal models with the same causal structure and the same distribution for the observed variables will always give the same causal effect. Clearly, if all variables, all relevant variables are observable, then it's always identifiable. But if you have this hidden variable, remember in the asymmetry paradox, now if this guy is hidden, a confounder, then this effect is not identifiable because we cannot determine the property of this causal link from their distributions, right? Due to the confounder. Okay, so I hope this is clear. Giving lecture on Zoom is really annoying because I cannot see your face, I cannot see your feedback, but I hope it's clear to you. And now, Professor Rubin from Harvard developed a potential outcome framework regarding whether we can identify causal effects. And Pearl, and also Peter Sberti at CMU, Pearl at UCLA, developed the graphical representations of the conditions. So here you can see the backdoor criterion is a graphical criterion, specific criterion that can be used to determine whether the causal effect of X on Y, some variables, is identifiable. So first, let's have a look at the backdoor. Probably I cannot give details. I will just explain what is relevant in this particular line of research, and then we'll have a quick look at why we care about causality when we do machine learning. So basically, backdoor criterion is, I should put it this way. Suppose a set of variables satisfy backdoor criterion, and then the causal effect will be identifiable. So if Z satisfies backdoor criterion relative to X, Y, ordered pair, then the causal effect of X and Y is identifiable by making use of this formula. And this is the front door criterion. Now you can see Z is not there, it's not on the back, it's not in front of back door, it's in front of front door relative to Y. And this is the front door criterion. So even if you have a confounder here for X, Y, because of this variable Z satisfying front door criterion, the causal effect of X and Y is identifiable by making use of this formula. And here you can see application. So even if you have a confounder, we can still identify the effect of smoking on lung cancer because of the additional variable Z, the TAR. Okay. Remember structural equation models. So here for simplicity, now I'm going to define potential outcome framework, but I'm going to define potential outcome and counterfactual variable. So for simplicity, suppose we have only two variables, X and Y. And right here, you can see the structural equation models. X is determined by something that is not in the system, and Y is determined by X and some noise, right? X causes Y. So, and we also have U. U is a particular experimental unit, say a person. And then for each unit, we have the value for EX and EY, say small EX and small EY. And then, now suppose we do intervention on X. We just set the value of X to small x. And accordingly, right? This is the first equation. And also the second equation will become this one because the variable x will become a small value of x. Okay, now potential outcome is this guy. It's the value of y given by this equation for unit u. If you are given unit u, then you have a specific value for this ey, right? So this is the definition of potential outcome. Now you can see if you have multiple values for x, 0 and 1, treatment control, right? Then at least for one of them, the potential outcome is not directly observable. Why? Because for a particular unit, for any unit, you can only do one particular intervention, right? You can intervene to set the value to 0, and then the potential outcome corresponding to value 1 is not observable. So, and sometimes we can also write potential outcome this way. So this is just a value of y, given intervention on x to set the value of x to small x for the unit u. If you just drop u here, then this is a variable because ey is random. Now this is called a counterfactual variable. And you can understand this variable as a description of the causal mechanism from x to y, because here x is fixed, right? You do intervention. You don't care about how x was generated. You only care about this mechanism. So this counterfactual variable represents the mechanism from x to y, or the mechanism to determine y by making use of the cause x. Then you can see the connection between the graphical criterion and the criterion in potential outcome framework. For instance, the backdoor criterion can be understood this way. So I've skipped this. Basically, it's related to conditional ignorability. They are equivalent. And there's also a unification of the criterion of the graphical criteria for identifiability for causal effects. Basically, a sufficient condition for identifying the causal effect from x to y is that there exists no bidirected path between x and any of its children. Here, by bidirected path, I mean a path with only bidirected edges. And by bidirected edge, I mean a confounder. So here is a bidirected edge. It just means that there's a confounder for x and y. Some C here as a common cause, direct common cause of x and y. And also there exists a necessary and sufficient condition that you can refer to this paper. But basically, you can quickly check whether the causal effect of x and y is identifiable by making use of the graphical representations. Okay, so I skip this. You can just verify that. And one thing I want to mention that the previous conditions apply non-parametrically. We don't have any parametric assumption. If you have parametric assumptions and linear models, then you can further refine the conditions. So in this case, if it's non-parametric, then the causal effect of x and y is not identifiable. But if linear, then it's identifiable. And causal effect is represented by alpha, the coefficient again. So one last thing regarding identification of causal effect is the propensity score. Suppose we want to see the average causal effect of x and y. So we have to do this, right? This is the distribution of y. This is the causal effect of x and y. We have to sum over C according to the probability distribution C, right? So if the two groups with different value of x have the same distribution PC, then it's easy. However, in many cases, we don't have that. If you have that, you are doing randomized controlled experiments. So distribution of C can be different across groups. How can we solve the problem? So we can either match the distribution of C, right? Usually it's very difficult because C can be very high dimensional. So one way to avoid that problem is to use the propensity score. Propensity score is defined this way. It's just a conditional distribution of x equal to 1 given the covariance, given all variables in C. Since C is a random variable, this is a random variable. However, this random variable is just a single random variable. It's not a random vector, it's a single random variable. Because this condition, because this property, which says x is independent from C, given the propensity score, we have the following result. So this causal effect right here can be rewritten in terms of H, the propensity score. Propensity score is just a single random variable. C can be a high-dimensional vector. That's why this guy is easier to calculate in most cases. And that's why we can, in many cases, we really benefit from this propensity score. Remember, propensity score is a function of C, and it's a random variable, but it's simple. Okay. And finally, I think we can either stop here or maybe you can stay here for another 3 minutes. We will stop. I will stop in 3 minutes. First of all, at the beginning, I gave some examples, some problems in machine learning. How can we solve the problem? Essentially, you can see the essential problem is that our decision process is different from machine decision process. How can we enable the machine to think in our way? Essentially, the machines must find a way to derive the hidden representation of the external world, right? We do so. We see different things. We want to find a unified view to explain all of them. This way, we can see the connection between different scenarios, and also we can see not only the connection, but we can also generalize our representations, and we can also automatically fill in missing information and so on. So the essential step is how we can build this hidden deep causal structure, right? By analyzing only the observed variables. A first method is factor analysis. Does not work here. And you can use the tetrad condition in the linear Gaussian case, and you can also use the triad condition and others in the linear non-Gaussian cases, and you can discover such structure from distribution changes. Regarding this, I think several groups are right now working on the problem. And if you solve the problem, then you can do unsupervised deep learning because you can derive those hidden concepts using disentanglement, right? The disentangled factors can be either the underlying noise terms or external input or the hidden representations. And you can deal with adversarial attack. Why? Because now the machines make use of the hidden features to make a decision, right? Instead of directly making use of the observed variables to make a decision. And this way, because you can encode the connection between different scenarios, it's easier to achieve the so-called artificial general intelligence. And regarding domain adaptation, I don't have time to talk about detail, but I just want to give you a simple illustration. Why we care about the causality, even if our goal is to do machine learning. However, if you do machine learning in the ID case, you can forget about causality. But in many cases, we have distribution shift, right? We have different variable sets, we have different sets of variables, and so on. Then we have to care about the causality. So suppose this is me. Right here, you can see my figure and you can see my shadow. Problem 1. Suppose you see my shadow. Can you say anything about my figure? According to your experience, you can say something, right? And you can even know that the light is from there. Okay. In contrast, suppose you see my figure, and suppose this is the new environment. You have no idea where the light is from. From my figure, can you say anything about my shadow? Regarding how long it is and in which direction it is and so on? You have no idea, right? So basically here the causal direction is from figure to shadow. Essentially it says the following thing: recovering cause from effects is simple. However, predicting effects from causes can be very difficult in these non-stationary environments. And fortunately, in machine learning, in most situations, the cause is actually the variable we want to estimate, right? Like in this example, the digit you want to write down, the label, is actually the cause of the digit you actually write down. And here, the disease is actually the cause of the symptoms, right? So you want to recover them. And you have cause here. That's why you can easily do domain adaptation. In light of that intuition, right? We can easily recover cause from effects. even if the environment is changing. The applications, and right here you can see what we should transfer in transfer learning. Essentially, we care about the causal mechanisms. In particular, we care about the invariant causal mechanisms. And right here, the take-home message that follows: causality is useful in transfer learning. However, it's not really needed, not really necessary, because finding causal model can be much harder than transfer learning. As long as you have a way to discover the property of changes of the joint distribution, you can do transfer learning. So this inspires this way, automatic transfer learning. So you have data set, right, different domains, and you can find a graphical representation to represent the changeability of the distribution regarding where the changes can happen, and and which modules are invariant, and then you can do adaptation. Adaptation can be understood as the following task. In the new domain, we have values for the features and we want to infer the value of y. So this is nothing but a problem of inference on graphical models. So this is just the end-to-end way to do a domain adaptation if you have multiple domains. Okay, to summarize, in this tutorial, I hope that I just made it clear why we care about the causality, what we can benefit from causality, and how we can learn causality. Regarding how we can learn causality, essentially we can make use of different types of independence. With conditional independence, we have the constraint-based methods. They are very general because they only rely on conditional independent relations. And with the independent noise condition, we can further find the causal asymmetry between two variables. As a consequence, we can even recover the whole DAG from observational data. And along this line of research, my colleagues in Germany and also some friends in Japan did a lot of work. And the last thing is to make use of independent changes. Essentially, if you have distribution shift, you can further make use of this property to discover causal information very easily. And you also had a very quick look at the identifiability and identification of causal effects. And finally, the remark is, even if you just want to do machine learning and data analysis, if the environment is complex, then usually you can benefit from causal modeling, because the causal model can allow us to go beyond the observed data, right? To have something very general, very fundamental that can be used to generalize. Okay, thank you very much. That's all.
Thank you very much, KUN.